So I'll be talking about graph databases, the foundations of it, the theoretical aspects of it, especially of query answering over graph databases. And there are two papers in which I was involved that I would like to suggest you in case you want to get deeper into this topic, okay? One of them, the first one of them is a paper that I wrote for a tutorial in POTS, in ACM POTS 2013, which is called Querying Graph Databases. And the other one is a paper published in the ACM Computing Surveys, okay? And this goes like really slowly into the different aspects of the theoretical background of query answering over graph databases. In case you are interested in this, and here you can find all the formalizations of the notions that we will be seeing during this talk. So my slides will be handwritten. I hope that my handwriting is okay, but in case you have doubts about what's written there, please stop me at any point. I'm also happy to take questions at any point as well. Well, first of all, I would like to do a quick review of some aspects of complexity theory and automata theory, especially of automata theory, since this is very important for the kind of results that we will be seeing over the lecture. Okay, so basics of complexity theory. Which kind of I'm not going into this, of course, right? But which kind of classes will be important for us? Definitely P and MP. I assume that that you have familiarity with these classes. And in terms of space complexity classes, we will also be talking about log space, yeah, deterministic space, deterministic log space, non-deterministic log space, which we will denote as L log space, and P space, which is polynomial space, right? So I'm assuming familiarity with all these things throughout the lecture. So just to recap, P is this class of what we think it is efficient. Of course, this doesn't coincide with reality, but what we think it is efficient. And then inside P, we have N log space. Inside N log space, we have log space. All these inclusions are not known to hold strictly, but we believe that they do. And P is contained in MP, this class here, and MP is indeed contained in P space. That is like the higher complexity class that we will be seeing. All right, so regarding automata and regular languages, what will be important for us? So we will be considering regular expressions over a given alphabet, sigma, and then the set of regular expressions is defined as by a grammar, which consists of the empty set here, the empty word. Each letter is a regular language, a regular expression, sorry. The disjunction of two regular expressions is also a regular expression. The concatenation of two regular expressions, which is denoted with this dot, but we typically don't write it down, is denoted in this way. And then we have the clean or transitive closure of a regular expression, right? So these are examples of regular expressions: A star, A B star, A plus B star, B, okay? So as we know, each regular expression is nothing else than a grammar, a syntax, and each regular expression is defining a language, yeah? What is a language? It's a set of words over the alphabet, sigma star, yeah? So the language defined by the empty regular expression is the empty language. The language defined by the empty word is the language that contains the empty word and nothing else. The language defined by the symbol A is the language that contains only one word, which is the word consisting of a single A. And then we have the inductive cases. The language defined by the union of two regular expressions R and R prime is the union of the languages. yeah, of R and R prime. The concatenation is those words that are formed by the concatenation of one word in the first regular language followed by a word in the second regular language. Yeah? And R star is nothing else than a concatenation an arbitrary number of times. Something important about R star to remember is that it always contains the empty word, right? So the empty word is always in the language of R star for R irregular expression. So now, what about examples, right? So the language of A star then is the language of words that are of even length, yeah? So words over the alphabet A that are of even length. AB star is nothing else than the language of words of the form, it's either the empty word or AB, 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 etc. And in this way, we can denote the languages of words that finish with a B, right? So something happens that it's either we see an A or a B. So I'm assuming that these are all the letters in the alphabet, and this word finishes with a B. So a simple cardinality argument shows that there are languages that are not regular. Yeah? So there are more languages than regular expressions. The set of languages is uncountable, and then the set of regular expressions is countable. But a different thing is to show that a particular language is not regular. And there are some important languages that are not regular. The prime example of this is A to the N, B to the N. Yeah? So words that have that are a bunch of A followed by a bunch of Bs in such a way that there is a one-to-one relationship between the A's and the B's. Yeah? This language is not regular because we would need infinite memory to keep track of how many A's we see before we start seeing B's. Yes? That's an intuition, of course, it's not a proof. Now, regular expressions are one side of this problem, but the other side is given by how to specify languages procedurally. Yes, and the way in which we specify languages procedurally is by using automata. Yes, and automata in regular languages will be very, very important in graph databases. Are very, very important in graph databases. So let's recall that an automata over finite alphabet sigma is a tuple A, which consists of a finite set of states. So it has finite memory. That's important bit here. An initial state Q sub 0 that belongs to the set of states. A distinguished set of final states, F, and a transition relation, right? So these transition relations contains all tuples Q, A, Q prime. Yes, for Q state, A a symbol, and Q prime another state, such that the automata is allowed to transition from state Q, reading letter A, to state Q prime. Yeah? So it's a transition relation because we are assuming that the automata is inherently non-deterministic. By definition, automata will be non-deterministic. So when we have a word, A1 to A7, a run of an automata on this word is a sequence of states. This sequence of states starts in the initial state, Q sub 0. This is the initial state of the automaton, and then runs through the word, reading every letter and producing another state that is allowed by the transition relation, right? So we start in Q0, we read A1, and we look at our transition relation delta, and we check for which states Q sub 1 this transition is possible. And then we move to Q sub 1. Yeah? And then from Q sub 1, we read A2, and we move to a Q sub 2 that is allowed. And this run is accepting if the final state, after reading all this word, belongs to the set of final states. Yeah? That's the idea. And the word then is accepted if there is an accepting run of this automata on this word. So since the automata is non-deterministic, the run is not necessarily unique. There might be multiple runs of an automata over a word, yeah? And then the automata accepts if at least one of these runs is accepting. Some other runs could be non-accepting, right? But if there exists a run that is accepting, then the word is accepting. And when the word is simply the empty word, then we say that the automata accepts this empty word if and only if the initial state is also a final state. Yeah. Now, when an automata is deterministic is when there exists a single run over every word. And how this can happen? Well, when for every state Q and every letter A, if we have two tuples of this form in the transition relation, then Q prime has to be equal to K2 prime, or we cannot have two different tuples of this form in delta. In this case, the automata is deterministic, and this tells us that there exists a unique run of a word, of an automata over a word. So this is an automata, for instance, that accepts the language A star. So I'll go quickly. What is important for us, for the sake of this lecture, is that if we start from a non-deterministic automata, an arbitrary automata, we can always build a deterministic automata that accepts exactly the same words, right? Having said in a different way, determinism doesn't, the languages accepted by automata are precisely the languages defined by deterministic automata. Yeah? That's important. And the second thing, the second bit that it's important is that there is a one-to-one relationship between the languages accepted by regular expressions and automata. The languages accepted by the regular expressions that we have defined as the regular languages are precisely those languages accepted by automata. More precisely, for every regular expression, there is an automaton that accepts exactly the same words. Yeah, and for every automaton, there is a regular expression that accepts precisely the same words. Yeah, and moreover, these relationships are constructive. For each automata, we can construct an equivalent regular expression, and for each regular expression, we can construct an equivalent automata. Now, the cost of these translations is different. The translation that is more important for us is the one from regular expressions into automata. And this can be carried out in linear time. And this is important. From a regular expression, we can construct an equivalent non-deterministic automaton in linear time. The other translation that we will not be using is much more expensive. Going from an automata into a regular expression actually takes exponential time in the worst case. But luckily, that's not the translation that we will be using. Okay. So complexity of some problems for automata, and this we will be using over the lecture, is what is, for instance, the complexity of checking whether an automata accepts some word, that is, the language is different from empty. This problem is L-log space complete. So it can be solved in non-deterministic log space, and it is complete for this class. Because what we have to do is to guess a path from an initial state to some final state in the automata. Right? It's a reachability problem, which are known to be L-log space complete. Yeah? Another problem, this we will not be using, but another problem that is L-log space complete for automata, for instance, is to check whether the language accepted by an automata is finite. Because what we have to do is to check over the automata whether there are cycles. Yeah? Cycles that are meaningful, in the sense that cycles that can be reached from an initial state and that can reach a final state in the end. Yeah? If that cycle exists, then the language is infinite. If it doesn't exist, then the language is finite. This we can check in L-log space as well. But there are some interesting problems for automata that are much more expensive. Yeah? One of them, for instance, is the containment of automata. Whether the language accepted by an automata A1 is contained in the language accepted by an automata A2. This problem is p-space complete. So it's much, much more expensive because essentially what we have to do is to complement. We have to complement one of these automata, and to complement one of the automata, we have to determinize it first, and that incurs us in an exponential blowup. Yeah? Another problem, well, similarly, whether two automata are equivalent, they accept exactly the same words. Yeah? Even the problem of checking whether an automata is universal, whether it accepts all existing words, which is the complement of this problem here. Sorry, no, it's not the complement. Sorry, it's related. So this problem is the emptiness problem. Yeah, this is n-log space complete. But the universality problem is p-space complete. So it's much, much harder. So this problem checks whether the complement of A1 is non-empty. Yeah. So this problem is p-space complete, and it's much more expensive than the emptiness. But most of the time, we will be considering this problem, the non-emptiness problem, yes, which can be solved in n-log space. So that's an important piece of information. And in fact, given an automata A, checking whether this automata accepts some word, not only is in n-log space, but can be solved in linear time using standard structures. Yeah? So depth first search, we can do it in linear time. Yeah? In the size of the automata. That means the number of states plus the size of the transition relation. Yes? So another thing is that we can carry out automata intersection in linear time. So what is automata intersection? We have A1 and A2, and we can construct this automata A1 cross A2 that accepts precisely the words that are accepted by both A1 and A2. Yeah? And how do we do it? We take the cross product of the set of states of both automaton. The initial state will be the ordered pair formed by both initial states, and then the transition relation is just the synchronization of both transition relations, right? This automata can be then constructed in linear time, in the linear time meaning the product of the sizes of these two automata. Yeah, that we will also be using throughout the lecture. Okay, any questions until here about automata? No? So let's start with what I think you will be more interested in, that is graph database. Graph databases, foundations of graph databases, starting with graph database models. So why graph databases are important? Graph databases are used in applications to represent semi-structured data. Yeah? And they are important in domains where the topology of the data, that is how the data is interconnected, is as important as the data itself. If you have a domain in which this is the case, then perhaps a graph database model will be useful for you. Yeah? So an example is a movie database, right? In which nodes are actors and movies, and then actors are linked to movies in which movies are linked if they have the director, for instance. Yeah? You can clearly represent this with a relational database, but this relational database will not be representing really the topology of the data. Yeah? This interlink. I mean, you want to traverse, you want to navigate this data, you want to visualize the structure of the data, and the way in which this could be done is by using a graph database. So the most general graph database model today, and the one that is actually used by commercial graph database engines, is that of property graphs. Yeah? And perhaps the simplest way to define or to understand what a property graph is with a simple example. Here there is a property graph. We have nodes and we have directed edges. each node and each edge is a small database. It's a small relational table. That's the way you can think about it. So each node has a unique identifier, right? This node is N1, this node is N2, this node is N3, and so on. But each node, and the same for edges, right? Each edge comes with its own identifier. Now, each node and each edge is labeled over a finite alphabet. Yeah, so we're saying a node is a person here. This node is a movie. This edge is of the type acts in. Yeah? And then each one of these nodes and edges can have 0 or more property value pairs. Yeah? So we can say, for instance, we can qualify the way in which Clint Eastwood acts in the movie Unforgiven. So we can say he acts in the role of Bill. The reference is IMDb. And by the way, he also directs this movie. But notice that this edge here has a label, but it's not qualified, right? There is no property values. And in this way, we say that and for this, we say that the model is semi-structured because we don't force all edges of the same label, all edges to contain property value pairs. And actually, we don't even force all edges of the same label to have the same property value, the same properties. Here in this example, it appears to be the case. I mean, like these two have the same things, these two have the same things, but that's not forced. Yeah? So is it clear what this graph database model is? I don't know if there are questions. I mean, like you can stop me at any point if you want. So very in a formal way, what a property graph is. A property graph is a tuple G, which consists of a finite set of nodes, B, a finite set of edge, these are IDs, right? We have node IDs, edge IDs. We have a function that labels each edge with an ordered pair of nodes that tells us, this function tells us where this edge starting and where it ends. Then we have a function that labels each node and each edge over a finite alphabet of labels. It tells us that lambda of this object O is the label of O. And then we have a partial function that takes either a node or an edge, and it takes a property from a set of properties, an infinite set of properties, and it associates a string. Yeah? So it's a partial function because not each property is defined for each node and edge. Yeah? So some functions only are assigned for some nodes and edge. So when we say sigma of OP is defined and takes value string W, what we're saying is that property P is defined for object O and takes value P. Yeah? Now, the model that it's used in practice today, that's where all practical query languages are, over which all practical languages like Cypher, for instance, are defined. But it's very general and very cumbersome to work with. The way in which, there is a question? Yes? It's given for this graph. So for this graph is a finite alphabet, right? So we would like to distinguish between this label, which comes from a finite alphabet, and that, and therefore we can query with some finite automata from the set of strings, which is infinite, and we don't know a priori, and that if we want to query with an automata, we will have to use more elaborate or more sophisticated automata models. That's the idea. Is it clear? Yeah. So this model is like really general and quite cumbersome to work with. So the way in which we tackle this complexity to work with to understand the basic theoretical aspects of graph databases is by taming a bit the model. No? So for theoretical exploration, we often consider a much simpler model of edge-label graphs. Yes? And you will immediately see the connection with automata here. An edge-label graph is nothing else than an automata seen in a different way, only that now we see it as a graph. So what will be a graph database for us in this talk? It will be a tuple G, which is an ordered pair of a finite set of nodes and a finite set of edge-label edges. Yeah. So each edge that goes from node B to node B prime is labeled with some finite symbol A from sigma. Yeah. So this sigma is fixed in advance. We know it, and we can query about it. Yeah? So we will write in this way when there is an edge label A from U to B in the graph. And here we see an example. This is an edge label graph. The names of the nodes are just for identification. They are not important for us in the model, right? So it's just the name, the node IDs, let's say. So we have authors, yeah? Researchers here. We have papers here. Each paper is created by one or more author, yeah? Then each paper is either appears in a journal, like this one, it appears in a journal, or is part of an edition of a conference. And instead, and also, the edition of a conference is part of the series of this conference, right? So conference can have several editions like this one, and each paper is part of a single edition, and each paper is created by one or more authors. Yeah? So this is a graph database, and this is the structure that we will be using. So what we are losing here, for the time being, we are losing all information about property value pairs. We are not using that. We are only using the topology of the data, the topological information that is present in the labels of the edges. Yeah. So what are the kind of problems that we will be considering? So problems investigated in graph databases are related to query languages. That is, languages, declarative languages used to retrieve data, to retrieve information from the graph database. And the kind of problems that we will be considering are expressive power. Which properties of models or graphs can be expressed in a given language? That's one of the questions we'll be considering. Query evaluation. Given a query Q and a graph database G and a tuple T of some sort, saying most of the time nodes, is this tuple in the evaluation of Q over G? Yeah, this is what is called the query evaluation problem. How complex, how hard it is to check whether a tuple belongs to the output of a query over a graph database. And something that is that it will appear in many of the works, but we will not be studying here, but I wanted to mention it anyways because it's important, and you will see in some of these papers if you read them, is the containment problem, right? So given queries Q and Q prime, is it the case that Q of G is contained in Q prime of G? Yeah, so this you use to check equivalence of queries, like when can you simplify a query in terms of another one because they are equivalent. Yeah? Now, if you think about it, there is a difference between problem 2 and problem 3. Yes, The difference is that in problem 2, we have the data available. There is a graph database, right? And we have to consider that. For problem 3, containment, there is no database available. What we are reasoning is about all graph databases, but the complexity will only be measured in terms of the queries. And queries are small, no? So when you talk about complexity of containment, you can allow yourself for high complexity, yeah, because the query is there. But for the problems that we will be considering about query evaluation, we have two aspects. We have the data and we have the query. Yes, and the data is much larger than the query, and we have to pay attention to that. Yeah? And the way we pay attention to that is by analyzing two flavors of complexity of query evaluation. Combined complexity is when the query queue is part of the input. That is, in a way, we are measuring the complexity both in terms of the size of the data, the size of the graph database, and the size of the query, and we are putting both parameters at the same level. They are equally important. Yeah? But we can also consider data complexity in which the query queue is fixed, right? So we can assume that its size is constant. And what is this trying to represent? Data complexity approaches the fact that D is large and Q is small, right? So the dependence on the size of the query should be considered differently than the measure on the size of about the size of the database. Yes.
What is large?
You wanted to kill me. No, it can be quite large, no? I don't know, Floris. Wim knows. Wikidata, yes. But that's very large, no? It is? Floris, you are. but for these companies like Facebook or Google that work with their own graph databases, they could probably even be larger. I don't know really. I don't know, but even larger than that, definitely. Yes. But Wim is the right person to answer this question since he has been more or less. But he has experience working with these query workloads over these graph databases. But I should know. Yeah. I proved in front of everyone that I'm a theoretician, you see? That's a proof. All right. I'll change to a different topic now. We will start looking at query languages. I don't know if there is any question at this point. Okay. So an essential feature behind practical, so you see, I'm practical. But this is true. An essential feature behind practical database languages is their ability to navigate the data. Yeah? So this is, in a way, what makes graph database different from relational databases. Yeah? So you have this. It's true that in SQL you also have recursive features, but here these recursive features are really first-class citizens of the languages. Yeah. So what do you want to do? You want to traverse paths in the graph database while checking if a certain condition holds. How much this is used in practice? This is something that it's worth studying, and Wim has done it. But at least some level of recursiveness is used in by people in practice, and that's the reason why these languages include these features. So what for us will be a path in a graph database is just a sequence of consecutive edges, right? So these are consecutive edges, but what is more important for us for a path is the label of this path, which is the concatenation of the symbols that appear in the edges. So the label of this path row, we will typically denote as lab of row, and it will be the concatenation of these symbols that form a word in our finite alphabet sigma. That's what, in terms of querying, we will be looking at. To start with, later we will be talking about more expressive things, but for the time being, we are only interested in this label. So for each node, if we have a single node, the sequence formed by that node itself is also a path, and the label of this path is the empty word, okay? So here we see a path in the graph database highlighted in colors blue, the nodes, and red edges. So this path goes from this paper here to the conference pods, and the edges are highlighted in red. So this is the path. So the most basic kind of language for expressing these properties about paths are called regular path queries, and they have been studied since the 80s. So regular path queries, which we will denote by RPQ, is an expression of the following form. We have two variables, x and y, and we have an edge between them that goes from x to y, but this edge is labeled with a regular expression over sigma. So it's not a single symbol like in a graph database, but it's an arbitrary regular expression. So for instance, the following are regular path queries over sigma equals a and b. So we can say x goes to y via this path label AA star, or x goes to y via this path label a plus b star b. Yeah? So it's an arbitrary regular expression over the set of labels that appear in the database. So what is the semantics of regular path queries? We are given a graph database and a regular path query queue, yeah, of this form over sigma. And the evaluation of Q on the graph database, which we will denote by Q of G, is the set of all pairs of nodes U and B such that there exists a certain kind of path, and we will be putting special attention to which kind of path. There exists a certain kind of path row from node U to node B in G such that the label of this path satisfies this regular expression N. So this query is saying, give me all pairs of nodes U and B such that there exists a certain kind of path that goes from U to B such that the label of that path satisfies the regular expression L. That's a regular path. Now, which kind of path? It depends on the semantics that you are considering. Different semantics are based on the class of paths allowed. You can have arbitrary path semantics. This is the one that is mostly studied in theoretical papers. Yeah? So any path is considered to be valid. You want to find whether there exists an arbitrary path from U to B whose label satisfies a given regular expression. Or, as it was studied in the beginning of graph databases, you can have a simple path semantics. If you want to find for flights from one city to another, you don't want to find flights that go twice over the same city. Yeah, that doesn't make sense, even if you are satisfying your regular expression, right? So you could have a semantics that is based on simple paths. Or a trail path semantics, that is the one that is essentially used by some graph database engines today, such as Neo4j and the language Cypher. Yeah? They use a trail path semantics. And what is a trail? A path that doesn't repeat edges. Yes? Okay, so here we have an example of a regular path query. We're asking for pairs of nodes X and Y such that there is a path between them that is labeled part of and series, right? So what is this selecting? It's selecting all pairs P and C such that P is a paper published in a conference C. So these are precisely the nodes in this in this graph database that satisfy this query. All pairs of nodes, all pairs of papers P and conference C such that they are linked by part of series. Yeah. This, of course, under any of the previous semantics, because this is not only an arbitrary path, it's a simple path and it is a trail. So in general, there is an inclusion between these semantics. If U and B is linked by a simple path labeled in L, then it is also linked by a trail labeled in L, right? So if you don't go twice over the same node, you cannot go twice over the same edge. And if you are linked by a trail labeled in L, then you are linked, of course, by an arbitrary path labeled in L. But the opposites are not true. So these semantics are one more restrictive than the next one. So for instance, here, there is a trail from S to T labeled ABAB. ABAB, it's a trail. You go twice over the same node, but you don't go twice over the same edge. However, there is no simple path from S to T labeled ABAB. Yes? And here, there is a path from S to T labeled ABABAB. You go twice over this cycle, but there is no trail from S to T labeled ABABAB. So there is an inclusion in terms of how restrictive these semantics are. Now, there is, of course, a need for inverses as well in this language. So far, we're only checking whether there exists a directed path that satisfies a regular expression. But imagine that we want to extract pairs A and C such that A is an author who published a paper in conference C. Yeah? So with a directed path, there is no way we can leave an author because all edges reach the authors. They point into authors. So one can prove that one cannot do this with regular path queries. Of course, this is very, very simple in this case. As edges labeled creator need to be traversed backwards. So this gives rise to the idea of defining regular path queries with inverses, or two-way regular path queries, which we denote by two RPQs. So we have a finite alphabet, and what we are going to do is to complete this alphabet with all possible inverses, A minus. So a two-way regular path query, a 2RPQ over sigma, is a query, is a regular path query over this extended alphabet. That's it. Yeah. So we have inverses. So for instance, we can say find all pairs that are linked by a path labeled AB, A minus, B minus, A. And how is this going to be interpreted? Well, since we extended the language graph database. And what we're going to do is each time we have an edge U goes to B labeled A, we're going to add the inverse edge that goes from B to U labeled A minus. Yes? So we are going to evaluate, now we evaluate our two-way regular path query as if it was a standard regular path query over this extended alphabet, over the completion of the graph database with all possible inverses. So now we can extract what we want. We can extract the pairs A and C such that A is an author that published in conference C. What do? We say creator minus part of and series. This will give us what we want. This, of course, under any of the previous semantics again. So what is the complexity of 2-RPQ evaluation? So what is the problem? Yes? Practical question? Yes, yes. It is the most intuitive. It has some very good properties, very close to the ones that arbitrary path semantics have. So that's the reason why I didn't want to introduce it, because it's very, very similar. But it also have some drawbacks in some cases. I mean, it might not be the most intuitive for some examples. Yes. So that's why I think it's useful for a practical graph database to give you flexibility at the moment of defining the semantics. Yes. Yeah. So arbitrary? Well, that's a query that's talking, yeah. So here we're talking about whether there exists a path that satisfies something, no? Yeah, and you want to know whether all paths satisfy something. Well, in that case, it's the negation of your of something, right? And then you have to extend the language. We will try to move into more expressive languages. I don't know if we will get that far, but of course you can study. There is a myriad of different languages, but so far it's just this existential semantics. Yeah. Yes. For the time being, yeah, you could have, and this is something that is allowed in Cypher, but we will not study this. What is RPQ evaluation then? You have a graph database, G. We have two nodes, S and T, and we want to know whether they belong to the output of this query. That is, we want to know whether there exists a certain kind of path that goes from S to T that is labeled L. What is the bottom line of what I will present next is that the complexity of RPQ evaluation depends very much on the path semantics that you are using. Yeah. So in order to distinguish the cases, we will talk about Q arbitrary of G, Q simple of G, Q trail of G, depending on whether we are outputting pairs of nodes linked by an arbitrary path that satisfies L, by a simple path that satisfies L, or by a trail that satisfies L. So let's start with an arbitrary path semantics. We want to check whether there exists from S to T this path rho whose label satisfies the regular expression L. What is the idea here? Well, first of all, L is a regular expression, so we can turn it in linear time into an automata. The graph itself is also an automata. We can see it as an automata with initial state S and with T, and then we can take the intersection of both. Yes? So more formally, we turn the regular expression L into an equivalent automata A sub L in linear time. Yeah, we can do this. This is what we mentioned at the beginning of the talk. We can see the graph database as an automaton, yeah, with initial state S, with final state T, and this will give us the words accepted by this automaton are precisely the labels of the paths from S to T in T. Yeah? And then we can construct the intersection of these two automata, the regular expression that is constraining which kind of paths we want, and the graph database. We take the intersection, and we can do this in linear time on both. And the words accepted by this intersection are those that label paths in G from S to T and belong to L. Yeah, so that's precisely what we want. So now we have a compact representation of all the words that accept that belong to this language. Yeah, in this automaton. And now the only thing that we have to do is to check this language, to check this automata for emptiness. Yes, because this automata encodes all the words that label these paths. So this we can do in linear time, and that's what we have. And then the problem of RPQ evaluation or 2 RPQ evaluation under the arbitrary path semantics can be solved in linear time. Yeah. I don't know if there are questions until there. Yes. A non-deterministic automata, and actually being very careful, you also need epsilon transition. Yeah. But that's fine because you can check non-emptiness for this in linear time. So whether you get a non-deterministic automata or deterministic automata in this case is not important for your complexity analysis. Yeah? Because yes, Floris. Yeah. You already have a compact representation of all the things, and then you can use this object to do a lot of stuff, enumeration, etc. I agree, and this is what it has been done. But we want to understand this very basic object that is like, this is our relational atom in graph database. We want to understand this relational atom first. Yes, but I agree. You can now do a lot of stuff with this object, and so it has been done. Yeah. So you can do it not just for this language. You can do it for conjunctions of these atoms. You can do it for as long as what you get is an automata, then you can use this object to do all the stuff, and that's how it is done. Now, what about the simple path semantics? And here things become quite difficult and interesting. Given a graph database, 2 nodes, we want to check whether there exists a simple path from S to T that is labeled with a word that satisfies it. That is, we want to check whether there exists a node that doesn't repeat, a path that doesn't repeat nodes whose label satisfies this regular expression. So regular path query evaluation under simple path semantics and in stark contrast with the arbitrary path semantics becomes NP complete even for a fixed query, even in data complexity. Yeah, and this is bad, right? This is complicated because if things are NP complete in data complexity, and data is very large, as we mentioned before, then you will not be able to solve this problem in full generality. Yeah? So why is this the case? Consider this regular path query. And already for this regular path query, the problem will be complicated. You want to check whether there exists a simple path from some node S to some node T, which is labeled AA star. So imagine that all edges are labeled A. What are you checking here? You're checking whether there exists a simple path of even length in a graph from node S to T. And this problem is NP complete. Yeah, that's it. Now, if you want to check whether there exists a simple path from S to T in a graph, that's trivial because it's equivalent to checking whether there exists a path, right? But to check whether there exists a simple path of even length is much more difficult because nothing tells you that if you have a simple path between 2 nodes, you will have one of even length, and you will have to look for it over an exponential number of potential paths. And this problem is NP complete. And in fact, there is a beautiful characterization of for which regular expression this problem can be solved in polynomial time or it is NP complete. So assuming that P is different from NP, the following are equivalent for each regular path query Q with L fixed. Q can be evaluated in polynomial time under the simple path semantics, and L can be expressed as a regular expression in this class. Let's call it phi sub TR. Where is this phi sub-tr. Well, these are the regular expressions that are built as the concatenation of a word, one sequential regular expressions that is defined here, and another word, or is the union of these things. Yeah. And what is a sequential regular expression is either a word or epsilon, or A. What is A? It's a subset of sigma. So this is the disjunction of the symbols in A. It says these symbols appear at least k times or 0 times. And this class is closed under concatenation. So as long as you are in this class, and I mean in this class, not syntactically, you are equivalent to a regular expression in this class, then you can solve the problem in polynomial time. Yeah? So for instance, if L is a finite regular language, then the problem of query evaluation under arbitrary path semantics for regular path queries will be in P. Yes, because it's a union of words, right? A single word is in this language, is in this class, a union of words. Remember that it doesn't matter how big is this union because it's data complexity. Yeah? Then will be in this language and it will be evaluated. You can express something like A star, B star plus epsilon or C star. Yeah? So you can do this in this language. But the language that we have, A star, there is no way you can express in this language. This can be proved. Yeah? So you have a precise, and this is very rare, right? And it's also very beautiful that you can characterize exactly the class of regular expressions for which evaluation under simple path semantics can be solved in polynomial time in data complexity, right? That's important. Yes. Yeah, it is a dichotomy. So what it shows actually is a trichotomy, no? If I remember well. So they have the case when this is log space, L log space, AC0, right? AC0, L log space, and NP complete, no? Yeah, so it's a trichotomy. It's very beautiful. Yeah. Now, for trail path semantics, and Wim worked on this, there is also a trichotomy, no? In data complexity. So there is also a precise characterization of tractability for evaluation of regular path queries under trail semantics. Yeah, I'll not give it here. It's less restrictive than for simple path semantics, but it also exists. But it's also NP hard, right? It can be NP hard. So both trail path semantics and simple path semantics are in general difficult to evaluate. Okay, so now going to more expressive languages, conjunctive regular path queries. Imagine that we want to extract pairs of authors who have a joint paper in a conference. I have until 3:45, no? No, that's fine. I'll take until 3. Yeah. No, but people get tired. Not me. Imagine you want to extract pairs of authors who have a joint paper in a conference. Yeah? This cannot be expressed with a two-way regular path query. So we want to find, for instance, Tarjan and Hopcroft have a joint, no, they don't. Ullman and Fejin have this joint paper in a conference, right? This one here. So imagine that we want to do this, we want to check whether this is the case with a two-way regular path query. So we will try to reverse this creator minus, and then first check whether it's a conference paper. Yeah, so we would have to check whether it's a conference paper. We have to check that there is an outcoming edge part of from this paper. And then we would like to traverse back to check the other author, right? But the problem is that when you traverse back, like we do here, you may go to a different paper. So you get lost in this path, right? And you may end up in a different author. So you may conclude in this way, for instance, that Bardi and Lipkin have a joint paper in a conference, which is not the case, at least in this graph data. Yeah? So this cannot be done with a two-way regular path query. The way in which this is solved is by introducing variables, right? Regular path queries have variables already. They say X and Y, but they are not used for anything, essentially. But once you start conjuncting, putting all these variables together and doing joining more than conjuncting, joining these variables, then you can express this. So what are we going to do? We're going to use the conjunction of 3 regular path queries and then project some of the variables used. Some of the variables will be just existentially quantified, and some other variables will be used in the output. Yes? Not that I know. It's more like a case-to-case analysis, but it's not very difficult, really. So what do we do? Yeah. Yeah, but this language is yeah. So it will not allow you to. Yeah. Sorry. So what you want to say is that give me all pairs of nodes, X and Y, such that there exists a U. And when you say this U, you are marking this U, right? So you don't get lost anymore. There exists a U and there exists a set, such that, first of all, paper U is a paper that was created by X. The same U was created by Y. And then there is an outcoming path from U, which is labeled part of series. And this tells us that it's a conference. Once we have this, we can express, once we evaluate this on the graph database, we get precisely what we want. That is the joint authors of conference papers. So in general, a conjunctive two-way regular path query, or C2RPQ over sigma, is an expression of this form, right? So it's a conjunction. It's several regular path queries, two-way regular path queries, but you can repeat variables. And when you repeat variables, then you're doing a conjunction, yes? So, and then you will project some of the variables that appear here, not all of them. In the previous example, U and Z were just existentially quantified. They were not used in the, there is a question or? Yes?
Yeah. Maybe I didn't understand, but why do you have to go back to the series though? And
you don't need to, you don't need to. You could just check part of, yes, yes. You don't need to, but you have to check something, no?
Yeah.
You have to check that it's a conference paper, no? No, not an arbitrary paper. Could be a journal paper as well, no? Yeah? So you don't have to go part of and then series. You could just go part of, but part of you have to check because otherwise it could be a journal paper and that you don't want to check. Yes?
Question, but I'm talking about the key that you have in the previous slide doesn't really
no, it cannot. It cannot, yes. So for doing that, you would have to introduce inequalities. But again, I want to present like the most basic language instead, yeah. So that we can study this most basic language, I mean, like the essential features of this most basic language. Yes, but of course it could return Bardi and Bardi, yes. And it will return Bardi and Ullman and Bardi as well, no? Bardi and Bardi, yes, yeah. But that you could, I mean, if you add some, light features to the language, you could do that. Well, the semantics is based on homomorphisms. I don't want to introduce it. I mean, like, the idea is clear, right? You want to find a mapping from the variables to the nodes of the graph database such that for each regular path query is satisfied in the I think it's kind of clear from the example. So here we see what is a matching, right? So this node gets mapped here, this node gets mapped there, and this node, the node U, which is exponentially quantified, get mapped there, and this one gets mapped there. Yeah, that's it. So now we have this problem, C2RPQ evaluation. We have a graph database, we have a conjunctive two-way regular path query, we have a tuple of nodes. Imagine that the query is Boolean, that is, it doesn't even have free variables. I mean, it doesn't have variables projected here. It doesn't, the complexity of the problem doesn't change. We want to check whether this query holds in the graph database, right? We want to check whether there exists some output possible. And this problem is actually NP complete. C2RPQ evaluation is NP complete. So for the time being, forget about whether we're thinking about the simple path semantics. We are thinking about the simplest semantic, the arbitrary path semantics, which is the simplest semantics in terms of complexity. So regular path query evaluation for arbitrary path semantics was tractable. You just compute it. But when you move to conjunctions, for the arbitrary path semantics, things become NP complete. And that's based on the presence of this variable. Why it is an NP? Well, it's simple. You just have to guess a matching from the variables into the graph database, and then you check each regular path query in isolation from this matching, which can be done in polynomial time. Yeah? Now, the intuition, why it's NP hard? We can use a simple reduction from tree colorability. You take an undirected graph, G, and we will construct a graph G and a CRPQQ such that G is tree colorable if and only if this query Q has at least some answer. That is, it can match into the graph data. And the idea is that you encode the graph into the CRPQ. The CRPQ has exactly the same structure as your graph. So that is, each time that we have two nodes that belong to an edge, we put a label, an edge label A from a variable representing this node to a variable representing this node. So you will have a lot of joins and a lot of structure in this query, no? And our graph database, H, will be something very simple. It will have just three nodes, one that we call blue, another one that we call black, and another one that we call red. Yeah? So you can go to any node from any node here by following a path labeled A. Yes? So it's quite easy to see that G is tree colorable if and only if there is some homomorphism from Q to G to H, right? Because what is a tree coloring of this graph? It's just a way to assign colors to the nodes in such a way that two adjacent nodes do not receive the same color. But that's exactly a possible homomorphism from this Q into this graph database, right? How do you map this Q into this graph database? You say each node goes to some color in such a way that if there exists an edge between two of these variables, which are nodes, they receive a different color. Yeah? So basically, it's the same problem, no? It's a homomorphism problem. So as a corollary, we get that C2RPQ evaluation is NP hard even if queries use no inverses. Yeah, without inverses, the problem is NP hard. all edges are labeled A, there are no regular expressions in queries save for a single symbol, A, and the graph database H is fixed. So the intuition here tells us that the complexity of evaluation comes from the structure of the C2RPQ, of the query, not from the data. Yeah? And this, as we mentioned before, is something that we want to avoid somehow. So we want to kind of distinguish between the complexity that depends on the data from the complexity that depends on the query. Yeah? So here the data was just a triangle. Yeah? And that's not really what we want to measure. So why? Because we are not, in this proof, we are not studying the data complexity. We're studying the combined complexity of this program. Yeah? What if we study the data complexity? Then the previous reduction doesn't help because the graph is fixed. So it doesn't tell us that C2RPQ evaluation is NP complete in data complexity. In fact, if the query is fixed, then we can reduce the complexity of evaluation. Sorry. Why we can reduce the complexity of evaluation? Because we only have to check for all possible matchings of the query, of the variables of the query into the graph database. How many such possible matchings you have? You have size of the graph database to the size of the query. Yeah? But now the size of the query is a fixed constant. So this means that this is polynomial. Yeah? It's not a very fair polynomial. This could be 6, 7, 8, whatever, right? But it's polynomial, it's fixed. Yeah? And then once you have this, everything else you can check in polynomial time. In fact, you can prove actually something stronger. It's not only in polynomial time, but it can be solved in n-log space in data complexity. So this shows that C2RPQ is not such a bad language after all. Yeah? So truly, it can be NP complete in combined complexity. But combined complexity is not really the right measure here, right? And it becomes polynomial, and in fact, n-log space, that means it's highly parallelizable in data complexity once you fix the size of the query. And this is a property that practical query languages like relational algebra or SQL, which is based on relational algebra, have. They have exactly the same kind of properties. They are polynomial in data complexity. Yes, Andre? It's yeah. With the simple path semantics, you are screwed since the very beginning. Yes. Yeah. Yeah. So from the very beginning, for C2RPQ. So essentially, for the rest of the talk, we got rid of the simple path semantics, not because it's not useful. It's very useful. Also, the trail path semantics is not only very useful, it's used. But in terms of the complexity analysis, complexity, you are screwed from the very beginning. So here, for arbitrary path semantics, a regular path query evaluation will be polynomial, but CRPQ evaluation will be NP complete, but in data complexity, it will be polynomial. Okay. Yes. Yeah, to the number of variables of Q, true. I'm going to talk a bit about that now. Yeah, so let me try to go over this and let's see whether it. What if we want to do efficient evaluation of C2RPQs? So evaluation of C2 RPQs is G to the size of the query, actually to the number of variables of the query. This is the naive algorithm, right? That's what the naive algorithm does. It's G to the number of variables of Q. This is polynomial if Q is fixed, but certainly not really practical if the number of variables in Q is, say, bigger than 4, and G is a large graph database, yeah? Very large. Imagine that, yeah? So it would be ideal if, at least for some CRPQs, and at least for some CRPQs that are used in practice, I'm sorry, we can evaluate them in time O to the G to some constant that is fixed times size of the query to some D. This is what is called the parameterized complexity, right? Whether we can do this in fixed parameter tractable time, for those who are familiar with parameterized complexity. So when can we do this? Well, essentially when we can bound the structural complexity of the query. So in particular, for acyclic CRPQs, this will be the case, and this will be essentially linear time complexity. So as we will explain next, and I'll go through this in 5 minutes since we have to stop, this is the case for the class of acyclic C2 RPQs. So in fact, we can actually prove something stronger for acyclic C2 RPQs. Evaluation of acyclic C2 RPQs can be solved in time, quadratic on the size of the graph database times log of the size of the graph database times the size of the query. So what is different here is that we have got rid of the size of the query in the exponent of the graph database. It will only depend on the size of the query here, right? And this is small, so this can be hidden somehow in this big O. So when a conjunctive two-way regular path query is acyclic, well, when we look at the undirected graph of its structure, of its nodes, then this is acyclic, but we don't have to take into consideration loops or parallel edges. Yeah, we assume that if two of these atoms connect the same variables, then there is just one edge between them. And if there exists a loop, say x sub I equals y sub I, then we will not consider it. I mean, we will consider that as acyclic. So for instance, this query here is acyclic. It has a loop, but we don't consider it. It has two parallel edges from x to y, but we don't consider them. Then the undirected graph is just a single edge. This is an acyclic C2 RPQ for us. But this one has a real cycle, right? It goes from x to y, then from y to z, and then from z back to x. It has a triangle, a directed triangle. This is, well, it has a triangle. It doesn't matter whether it's directed or not. So it's not acyclic. So in 3 minutes, better. I think that the intuition is more important here than the proof. This is what we call the joint tree of an acyclic CRPQ, right? So it's acyclic, so we can see it in this way. The idea is that you can go inductively by a bottom-up procedure computing the set of values of possible homomorphisms from the query induced by all variables that are below this node, yeah, into the graph database. So now at some point, for instance, you have all possible values of homomorphisms from the query induced by only this variable. And you have all possible values of homomorphisms induced only by this variable, yeah? And now you'll compute all possible values of homomorphisms from U for U for the query induced by these variables, U, W, and L. So what is the subquery induced by these variables? It will be this atom and this atom. Yeah, so you will reduce to this part of the query, you will compute what you have there, and you will project what you have, all possible outputs into U, and then you continue iteratively. Why you can do that? Because the output here in set only depends on what you have on U, what you have on B, because here you have collected all the information that you needed from what is below this. You have all the information that you needed from this in U, you have all the information that you needed from this in B, and now what you need to compute what is set, it only depends on U, on B, and the things that are between set and U and between set and B. And this you can compute in polynomial time. That's the idea. So you take advantage of the structure of the query to compute inductively in a with a bottom-up procedure the set of homomorphisms from the query into the graph data. Okay, so let us recall that we were trying to find efficient subclasses of C2RPQs. And by efficient in this case, we mean something that it's not only efficient in data complexity, but can be evaluated in polynomial time in the size of the graph database, and something that depends on the query, right? So we have split the dependence on the graph database from the dependence on the query. Yeah, and what we notice is that as long as the query is acyclic, then we can solve this problem in polynomial time with the required condition on the dependence on the query and the dependence on the graph database. But there is another way in which we can do this by actually not using variables at all in the C2RPQs. And this is what we call the class of nested regular expressions, which are based on propositional dynamic logic, for those who know, or XPath, which is a language for querying XML documents. So let's say that a C2RPQ, as before, is strongly acyclic if, first of all, it doesn't have loops. So before, acyclic queries allow loops and parallel edges, but we will say that they are strongly acyclic when, in addition, we have no loops and we have no parallel edges. So nested regular expressions will extend the class of strongly acyclic C2RPQs with existential tests a la XPath. But we will not mention variables. So they have been used to answer queries in RDF, which is this data model for the semantic web under RDF schemas, for instance, this class of nested regular expressions. So a nested regular expression is really an extension of the class of regular path queries. What does it do? Well, we have all things that we have in regular path queries, plus this existential test. So we have the empty set, the empty word, we have symbol say, inverses, we have union, we have concatenation, we have clean star, but we also have an existential test. So the following are nested regular expressions over sigma ABC. For instance, we can ask A star nesting B, C, or we can ask A nesting B, C, all of these starred. Yeah? So what is the evaluation of a nested regular expression on a graph database? Well, until here, it's exactly the same than the evaluation of a regular expression of a regular path query, but we also have these existential tests. So what does existential test do? They check for pairs U and U such that B, some B, can be reached by following N1, right? So we do at the node U, we do an existential test of whether we can reach some node B, yes, and that's where we have existential quantification, but only implicitly, whether we can reach some B from U such that the path from U to B meets the nested regular expression N1. Yeah? So for instance, we can express some C2RPQs with a nested regular expression. This, remember, that was the C2RPQ that gives us pairs of authors that have a joint conference paper. No? This is how we wrote it. But now we can express this without using variables with the use of a nested regular expression. The only thing that we have to say is creator minus, right? Creator minus, followed by an existential test. That what does it do? It checks from this node whether there exists a path labeled part of series, but stays in this node, right? It doesn't leave this node. And then it checks whether it can reach another author, in this case, Bardi, with the creator edge. Yeah, so that's the power of these existential tests. So now what we said is that every strongly acyclic C2RPQs, which is also connected, can be expressed as an equivalent nested regular expression of some form. Yes, but the good thing is that the class of strongly acyclic C2RPQs is extended, is generalized by the class of nested regular expressions. Yeah? So that in terms of expressive power. Yeah? So it generalizes a subclass of C2RPQs. In turn, the expressive power of the nested regular expressions is not subsumed by that of the C2RPQs, or even a union of C2RPQs in this case. So why is this the case? Because with a nested regular expression of this form, A, B, A, B, A, B, we can check for the existence of a path of A's from S to T, such that at each point there is an outgoing edge labeled B. Yeah, and this is something that we cannot check for a C2RPQ. So what do we have? We have that nested regular expressions extend the class of strongly acyclic C2RPQs, and yet they move beyond C2RPQs in general. So they are kind of incomparable in this case. Now, what is good about nested regular expressions? They keep the same properties of the regular path queries for the arbitrary path semantics, remember that, in terms of complexity of evaluation. That is, the problem of checking if a pair of nodes S and T belongs to the output of a nested regular expression on a graph database can be solved in linear time, that is, size of the graph database times size of the nested regular expression. Yeah? And this is somehow the most expressive language that we know that has this property that can be evaluated in linear time over graph database. Yeah? So once you add loops, things become difficult. Once you add parallel edges, things become quadratic. Yeah? And so on. So we would like to, so this is a very good property of nested regular expressions, that they have a very good balance between expressive power and complexity of evaluation. Yeah. Questions so far? Okay. So I'm going to talk now about graphs with data. Yeah. So graph databases as we define them, only talk about, only care about the query languages that we have been considering, only take care about the topology of the data, that is the edge labels, yes? So, but what about adding data then? Remember that the model of property graphs had a lot of data. Each node and each edge was a small database, yeah? So how are we gonna model that without going into the whole very expressive model of property graphs? We're gonna have a very simple extension of edge label graphs, which we call data graphs. So we will use a simple data model that is used to handle data at the level of nodes exclusively. So a data graph over sigma will be a tuple G, B, E, and alpha, where B and E is a graph database over sigma as before, and alpha is a function that assigns a bit of data to each node. And what kind of data will assign? It will assign a natural number. Yeah, so this will be the data carried out by each node. So the important thing here is that we can have two different nodes that carry the same value in terms of alpha. Yeah, so we can have this is what we call the data value of a node. We can have two nodes with the same data value. So here we have an example. We have this graph. We have the edge labels as before, but now each node carries a piece of data. And in this case, these three nodes carry the same piece of data. This carries a different piece of data, and this carries a different piece of data. So what we will be interested when querying this kind of models is the paths that combine data with topology. So if this is a path here, B1, A1, B2, A2, B3, and A1, A2, A7 is the label of this path, we, in this case, will be interested in the data path. Yeah. So this will be, the data path will be the following. For each node, it will replace the node with its data value, its natural number that labels this node. And then it will be followed by the label, then the data value, and so on. Yeah? So query languages for data graphs aim at checking properties over its data paths. Before we did it over paths, now we do it over data paths. However, even some simple properties are intractable in this setting, regardless of which semantic are we considering. So even for the arbitrary path semantics, there are some simple properties that become intractable in this case. Imagine the following property. We want to check whether there exists a data path from S to G such that all data values in this data path are different. This problem is NP-complete. Yeah? So why essentially this problem is NP-complete? Because we can reduce from the NP-complete problem of two disjoint paths. So we have two, remember that this is the following problem. Given a graph G, nodes S1, T1, S2, T2, add the paths row 1 from S1 to T1 and row 2 from S2 to T2, such that these paths share no vertices. This is the problem of disjoint paths. This problem can be easily encoded in our problem. So what do? We put two copies of the same graph. Each node receives a different data value, yeah, in each one of these copies, but the same node in this copy, the copy of a node here receives the same data value that the copy of the node here. And then there exists a path from S1 to T2 in this graph that doesn't repeat data values if and only if there exists disjoint path from S1 to T1 and S2 to T2. Yeah, so this problem is NP complete, and this simple property, then it's NP complete. So what is the conclusion behind this negative result? That if we want to have a query language for data graphs that is tractable in data complexity, it cannot express this property, right? This is a limiting property. This property, this is a constraint, right? This property is NP complete. If a language expresses it, it will be NP complete in data complexity, and that's bad for us. It's an arbitrary choice. You just haven't, yeah, absolutely. Of course, then you can move to more expressive models in which you can compare. Here you can compare essentially data values just for equality or inequality, no? But you could have, and people have studied more expressive models, and you can compare things based on arithmetic properties, for instance, of the data values or ordering, etc. And then you need some specific domains, yes. But for now, we just think that it's an uncountable model, and that you can check things just for equality or inequality. Yeah? So, yeah.
So if we don't worry about practicability, does it make sense to talk about like infinite paths with key or parity?
Well, no. Here, this is not the kind of properties that one would like to check. This is more related to model checking, for instance, no. But here, no. The paths are finite. Yeah. So you don't wanna check things about infinite paths.
And in your language, you can compare.
Yes. I haven't defined. Yeah, but this canonical property is, of course, the one that defines the class, and like Turing machine. The way in which you encode this is not so natural, but you can do it. Yeah. So what we did then was we had this logic of REMs, which has good properties in terms of data complexity. Yeah, it's in log space. And we had this other logic, work logic, that it's very, very expressive, yet the complexity is awful. Yes. And we wanted to try to bridge between the two worlds. Yeah. So we wanted to have something that is more expressive than REMs, and yet it has better complexity than work logic. And the idea we came out with was trying to close REMs under node quantification, path quantification, and register quantification. So, and this is related to a previous question on whether you could have negation for all paths. This is something that you can express in this logic with negation. So what is in this register logic, which I find appealing because it's simple to define and it has a decent complexity? Not really practical. No? I mean, from a theoretical point of view, this is not a practical logic, but I think it's a cute logic. You can say that two atoms are cute language, I should say. It's a cute language, not a cute logic. It's a language. You can say that two variables are the same. You can say that two paths are the same, two data paths. You can say that two register values are the same. Yeah, so remember that this is an extension of REM, so you have extensions of your registers. So at any point, the value in the registers are equal. You can say that the value of the registers are completely empty at one point. You can say that two nodes X and Y are linked by path pi. And you can say that I can read path pi from register value nu to register value nu prime by conforming to REM E. These are my atoms. Yeah. So this These are based on REMs, but you can compare paths, you can compare register values, and so on. And then what do you have? You have that your logic is defined by your atoms. It's closed under Boolean combinations, and it's closed under quantification over nodes. You can say there exists a node such that phi. You can say that there exists a path such that phi. And you can say that there exists a register value such that phi. So the semantics will be standard. Yeah. So, but which kind of properties can you express here? I'll not try to get into this because I mean, like, we don't have so much time, and it's a bit complicated. Diego, you have to go to. So we can express the following. We can express to whether there exists a path rho from X to Y and a node set such that for every node B in rho, path from such a node B to set. Yeah, so essentially something like this. It exists, I don't know if it is so visible, but from X to Y, and there exists a node set such that each one of these nodes reaches set. Yeah. So this is something that is expressible in the logic via a combination of quantification over registers and universal quantification. Yes. So what is the complexity of this logic? Well, this regular logic evaluation is XP space complete in terms of combined complexity, and it's P space complete in data complexity. That's what it makes it not practical, right? P space complete in data complexity is not good, but at least I think that it's a good logic. So unlike walk logic, this is elementary in combined complexity. Yeah? But unfortunately, data complexity is still quite high. However, the positive fragment of register logic admits efficient evaluation in data complexity. So this gives us a way to extend REMs with extra expressive power, retaining the good complexity of this logic. Is it? I hope it is more or less clear what this logic does and what are its properties. So questions until here, because I will move to a different set of slides. Okay, something that has appeared here somehow is that conjunctive regular path queries fall short of expressive power for applications that need to include paths in the output of a query. That's something Floris mentioned before, and to define complex relationships among labels of paths. And there are many examples in which this is needed. For instance, for semantic web queries, you want to establish semantic associations between different paths in the RDF database. In biological applications, you would like to compare paths based on similarity, for instance. In route finding applications, you would like to compare paths based on length or number of occurrences of labels. And data provenance and semantic search over the web, you may want to require returning paths to the user. Yeah. So these are all functionalities or capabilities that are not present in the languages that we have seen so far. So what we developed was an idea to compare paths in graph databases. And what we used was relations on words. Instead of using regular languages on words, we use regular relations on words. So example, our set of relations on word may contain unary relations like regular languages, context-free languages, etc. But also binary relations. We could check, for instance, if a path, whether a certain path is a prefix of another path, or whether two paths have equal length, or whether one is a subsequence of another path. So then we could compare among labels of paths in graph database. We could check, for instance, whether this is a substring of this of this other path. So in general, we will assume that S contains at least all regular languages. So what will be our S extended CRPQs? There will be rules as before, but instead of having regular expressions there, we will have path variables, and they can be repeated if we want. Then we will be able to compare paths in terms of pairs or even tuples of paths in terms of pertinence to some relations. And we will be able to project some tuples of paths in the output as well. So we may want to retrieve paths, not just nodes. So here there is an example. No, before the example, I'll try to explain how to express comparisons among paths using extensions of the class of regular languages. Regular relations. What are regular relations? They are regular languages for relations of any arity. So reg will be the class of regular relations, and ECRPQ of reg will be this extension of regular languages with these regular expressions. So in any array regular relations are sets of tuples of strings accepted by a synchronous automaton over the extended cross-product alphabet. So the input strings are written in n tapes. Shorter strings are paired with a symbol bottom, and at each step, the automaton will simultaneously read next symbol on each tape. So this is as follows. Imagine that we have n words, W1, W2, W3, Wn. They are written horizontally. So some strings are shorter than others, so we will pad them with this extra symbol, and then our automaton will start reading from left to right. It will read this letter, which is the cross product of all the letters there. Then based on the state in which this automaton is and the letter is reading, it will move to the second letter and so on until it reaches the end. Yeah? So now an automata can read pairs of words, it can read triples of words, and so on. So what are examples of regular relations? Well, all regular languages are regular relations of arity 1. But the prefix relation is also a regular relation. Why is it a regular relation? Because the only thing that we have to check is that we see the same symbol in both words until one of the words we start seeing the symbol bottom. So we can read in parallel. If both words have the same symbol, we keep moving until one of the words finishes. Yeah? And then we say that one is a prefix of the other. We can also check with the regular relation whether two words are of equal length. No? The only thing that we have to do is to check that we never see the bottom symbol. Yeah, they have the same length. But more interesting stuff can also be expressed. For instance, for any fixed k, we have all pairs of words or strings that are edit distance at most k. This is something that we can do, and this is a relation that is important, for instance, when comparing biological sequence, edit distance. No? Now, there are many interesting relations that are not regular, and these include the subsequence, the subword, the suffix relations. These things are not regular. So prefix relation is regular, suffix relation is not regular. So what we did study was the class of queries that are of this form. Yeah? So they take conjunctions of atoms, and then we can check whether some tuples of paths satisfy some regular relations. Look at this query. It says the following. I want all pairs of nodes x and y such that there exists an intermediate set for which we can reach set from x via path pi 1. We can reach y from set via path pi 2. The path pi 1 is completely labeled in A star. The path pi 2 is completely labeled in B star, and yet the lengths of these two paths are equal. So what am I outputting with this? They are comparing pairs of nodes linked by a path labeled in A to the n, B to the n, no? So this shows that these ECRPQs very easily move beyond the class of regular path queries and in fact of conjunctive regular path queries. Yeah, because remember that this language is not regular. No? So in terms of expressive power, this extends the class of CRPQs even with this simple query. So what is to be mentioned about the complexity of evaluation for ECRPQs? Well, extending conjunctive regular path queries with regular relations is free in data complexity. So the evaluation problem for ECRPQs with regular relation is still in n-log space in data complexity. In terms of combined complexity, is space complete, but this is not too bad. Yeah? I'm thinking whether, yeah, I'll mention a bit about. So, but what about more expressive things like subsequence or suffix? So ECRPQs with regular relation are still short of expressive power for some applications, say RDF or biological networks. They can compare string based on subsequence or subword. Yeah? These relations are rational. They are not regular. They are accepted by asynchronous automata. The problem is that once you add this, once you start adding these to ECRPQs, then the evaluation becomes undesirable or very high. So what is an n-ary rational relation instead of a regular relation? It's a set of n tuples of strings accepted by asynchronous automata with n heads. So as before, the input strings are written in the n tapes, yeah, horizontally, but at each step, the automata enters a new step and moves some tape heads, so it can move asynchronously between the tapes. So an n-ary rational relation is derived by a regular expression over the alphabet sigma union the empty symbol, which means you're not moving that tape, that head in that tape. So for instance, the subsequence relation is rational. The only thing that you have to check is that, and I mean scatter subsequence, yeah? I mean scatter subsequence here, that you can synchronize the whole word. The subword relation is also rational. Because what you have to check, that you can guess a point in which the two words start synchronizing, right? So you go up to the middle of the first word, you start reading the other one, you read it completely, and then you synchronize. But then, once you extend CRPQs with these rational relations that might be practical in some cases, things become really difficult. So if you extend eCRPQs with subword, then this becomes undecidable. So as long as you add subword, then things become undecidable. And if you add a subsequence, then things are decidable, but non-primitive recursive. So not even non-elementary, non-primitive recursive. This is even more difficult than that, even in data complexity. Yeah. So this really comes at a cost, and then there are different ways in which you can try to restrict the shape of the queries or the class of things that you add to them in order to get polynomial time things. And for the sake of time and the reception that we have to go, I'll finish here and leave some room for questions if there are any. Thanks very much. Diego, right in time.